program. And he's working under the supervision of Paweł Pietrukowicz, and Joachim is graduated from this university, was working previously with Igor Soszyński on variable stars, and now he's still following the variable stars phenomenon, but working on the BLAPs based on OGLE data, and that's the topic of his talk. So the floor is yours.
Thank you for the introduction. And today I will talk about the BLAPs, which actually maybe it's the time to decipher this name. So BLAPs stand for Blue Large-Amplitude Pulsators, and I will talk how the OGLE data contributes in research on this group of stars. So first I will talk about the discovery of this class. Then I will talk briefly about the history of detecting new objects of this class. Then I will present some ideas about the theoretical explanation for BLAPs, and in the end I will talk about OGLE discoveries. So the first object actually was detected in OGLE 3 data in the galactic disk around 2012, and this object was initially classified as a delta Scuti variable, but it was noted that it had unusually short period and large amplitude for a delta Scuti star. And soon after, there was a spectrum of this object was made in the Magellan telescope, and then it turned out that it is way too hot to be a delta Scuti star. Generally, it turned out that it cannot be a delta Scuti star, and it because it also had enriched helium abundance and also higher surface gravity, and from time resolved spectra, as you can see here, during two phases of the light curve, it could be seen that temperature changes, and this actually led to believe that this object is a pulsating star. Then another 13 similar objects were found in the inner galactic bulge, and some of these objects also had spectra taken. This was indeed 2016, and this generally led to establishment of this new class of variables. So generally, as the name suggests, they are blue, they have large amplitude of pulsations. And also the periods were in range from like 20 to 40 minutes. So generally, this stars, the idea was that they pulsate in the fundamental radial mode. They light blue are the main sequence, but they are slightly more luminous than subdwarf star, variable subdwarfs, and generally the mechanism of pulsations was attributed to the Z-bump, which was actually also there was an idea about radial limitation of iron group metals. So that was the proposed mechanisms of pulsations in this new class of stars. So then in 2019, 4 other objects were detected in the ZTF data. So these objects were named high gravity BLAPs because they had higher surface gravities, and some time resolved spectra were also taken with like radial velocities and temperatures to be determined. And generally these objects, it is important that they pulsate at much shorter periods, around a few minutes, as you can see here. Also, the helium abundances were different than in the so-called classical BLAPs, because these objects had much less helium in their spectra. But generally, these objects the main idea was that they could be the same class, but just more these objects were more similar to the hot subblurs in terms of surface gravity. So then in 2022, 22 candidates were found using the Gaia and ZTF combined data. So generally, they reddened stars using the green maps, and they got the distances from the Gaia DR2, and they checked for periodicity in all of blue objects. And then they found 22 candidates, denoting some of them as high confidence candidates based on spectral measurements, and 6 of those candidates were actually candidates for like high gravity BLAPs. You can see them here. But generally the spectra were like low resolution spectra, so only some of these candidates were denoted as high confidence ones. So then also in 2022, BLAP was found in the test data in a binary system with a blue type sequence star. And actually, the binarity was found due to time travel effects from the main test light curve. And this object also had like a typical light curve for a BLAP with a typical period around half an hour. So this was actually first such object. Then also in 2022, 4 other BLAPs were found in the Omega Wide survey, which uses VST telescope. And here you can see example light curves of some of the objects they found. And actually from these objects, only this object was classified as BLAP. All of the other objects were classified as some type of pulsating subblurs. And they also made an effort to put BLAPs in the HR diagram, but generally you can see that they are separate from other types of pulsating stars like subdwarfs and binaries, but generally they were only using like Gaia data to do this. So so this is not very precise, maybe. Then in 2023, one object was detected because this is actually one of the previously found candidates, but they detected it independently in the TMTS data, which is a Chinese telescope. And also they, at that time, they thought that this object is unique because it has 18.9 minute period, and this was suspected to be in the period gap between the high gravity and classical BLAPs. But actually this was later, the existence of this period gap was later disproven. And also they suspected that this object might be in a wide binary with period around 1,500 days, but this is, they stated that this is not certain. And another object was found in the SkyMapper survey. Based on generally they did some photometry of blue objects from the Galactic bulge, and they found this is example of the object that they found, and actually they made a spectrum of this object, and the spectrum was actually revealed like high temperature, typical for BLAPs, and typical gravity, but atypical helium content for BLAP within this period. So, and now a few words about theories regarding BLAPs. So, generally at first there were 3 theories about the internal structure of BLAPs. So, the first theory was stating that the BLAPs are 3 white dwarfs with shell hydrogen burning. So, but actually this theory predicted that period changes in BLAPs should be at least an order of magnitude higher than in observed ones. So then there are another theories about the core helium burning, and also this set of these theories, actually the main factor that would distinguish between them was the mass of the object. So like one set of theories predicted that the mass should be around 0.3 solar masses, and the other that should be higher, actually around 0.7 solar masses. Then there were like few ideas about the origin of BLAPs. At first, in 2017, there was this idea that BLAP could be like that BLAP could previously pass through near the supermassive black hole in the Milky Way center. But then there were other ideas. For example, in 2020, there was this idea that BLAP could emerge from a binary system with single degenerate type 1a supernovae, because the supernovae would blow away the outer layers of the star, which would, after some time, could pass through the BLAP instability area. Because generally, it is worth also to say that the BLAPs couldn't, they couldn't emerge as a product of evolution of single star, because the helium content was too high for this to happen. So then there was another idea about the BLAPs as a product of white dwarf and main sequence mergers, also in binary systems. They predicted some evolutionary tracks, and also they predicted the split in the helium contents. So here you have the high gravity BLAPs and the classical BLAPs, because this was work from 2023, so only this many objects are known. So, but they generally assumed that the scenario, like there are some models that predict the observed ratios. So then there was a study about the OGLE BLAP 009, which was one of the brightest objects of this class, and generally they did some high-speed photometry and time-resolved spectroscopy, and they found out the precise range of parameters for this object. And the most important ones is probably the luminosity is around 170 solar luminosities, because this is also one of the closest BLAPs with actually this parallax value below, even if it's below like 1 milliarc second, it's still one of the highest values for like BLAPs, because generally BLAPs are distant objects. So then there was another theoretical work that predicted where exactly the BLAP instability area is. So they made some models and predicted which type of pulsations could occur at which mass. They actually predicted that the most favorable scenario from at least from their models was that of like 0.7 solar masses. That was the conclusion of their work. And then there was another idea that the BLAPs could emerge as a result of two like extremely low mass white dwarf mergers. They did some simulations with MESA, and they actually had a set of three types of models with like these are the masses of the resulting like merger, like the object after the merger, and they modeled some initial masses of those systems that could produce such pairs of white dwarfs with like this type of star formation ratio. And generally, the conclusion was that BLAPs could emerge from such systems, but the predicted number of BLAPs in the Milky Way was like a few hundred. So generally, as we will see later, this is probably this model couldn't explain all of the BLAPs. Also 2 of the BLAPs actually were found to be a magnetic BLAPs because they show some equidistant frequencies in their frequency spectrum, and this was attributed to the idea that the rotational axis is not aligned with a magnetic axis, and this results in some additional frequencies. Now a few words about OGLE. So OGLE is the largest variability sky survey. Generally, OGLE observed over 2 billion sources, or still observes. The main areas are the Milky Way plane and the Magellanic Clouds. OGLE found over 1 million variable stars, and at least for now, it is still the largest variability survey. So now history of OGLE discoveries of BLAPs. We have the number of new objects. So these are the 14 objects that were used to with the definition of the class. And then in the bracket, you have the number of new objects. So this is obviously the same. Then in 2023, the galactic disk was checked for short periodic variables, and I actually found 25 BLAPs in the disk, and 20 of those BLAPs were new objects that were previously unknown. And actually, this may be worth to mention that in the disk, OGLE has in the majority of fields around at most 200 observations, or had at that time. So generally, the disk is also covered in the shallow survey. Then in 2023, but the publication year is 24, another 23 objects were published in the inner galactic bulge. So these objects were actually known for some time, but they didn't have spectra, for example. So yeah, then also actually in 2024, outer bulge was checked for. So this is the pink area, was checked for short period variables, and 33 BLAPs were found, and 31 of them were new discoveries. Generally, the number of stars in the galactic disk, there were more than 1 billion sources, around 1.1 billion sources. In the inner bulge, there's around 400 million, and in the outer bulge, around 700 million stars. So all of these stars were checked for short periodicity with a frequency up to 500 cycles per day. So now the most recent work, the inner bulge, was actually checked to finish the collection, and I actually found 90 BLAPs in there that were 88 of them were unknown previously. So this is to the addition to like 36 BLAPs, because one of this is from the disk. So here you have like distribution on the sky of BLAPs, and you can clearly see that they concentrate around the galactic plane. So a few words about the disk search. These are example light curves and color magnitude diagrams for the objects. So few interesting objects maybe. So this object had a unusually long period for a BLAP, but it was confirmed spectroscopically. Also, this object with pulsation period of 8 minutes was the shortest periodic variable detected in OGLE at that time. So, for example, you can also see like period changes in the light curves, but generally, as you can see, there are not at best few hundred observations for those objects over the decade-long light curves. Then the outer galactic bulge research, so 33 objects from 700 million stars. And here you have an example of the light curves. As you can see, there are objects that are in the suspected period gap. For example, with this, like BLAP 77, BLAP 65 are in the so-called period gap. So this actually disproves that this period gap exists. But actually these objects, we don't have parameters for them, so it is unclear whether they are similar to classical BLAPs or to the high gravity ones. So then the work from the inner bulge. So this is, as you can see from the light curves, this area has much more measurements, up to some like 15,000 or even more. So for some of the fields, of course, and 23 objects were detected with 22 new objects. One of the objects, for example, with such a coverage, we could see how its amplitude and period changes over the different seasons. And also this in this work, there were spectra were made for many of the objects, and this led to some interesting results. So here you can see that BLAPs obey a period gravity relation, which is expected. Then you can see that the split in like helium rich and helium poor, or like the helium rich are the classical BLAPs, so the longer period ones, and helium poor for most of the objects, and helium poor are the HG BLAPs. So generally here with the blue color, there are HG BLAPs are marked. With the green color, there are like TMTS BLAP and Sky Mapper BLAP, and also OGLE BLAP 009. And with the red color, all of the OGLE BLAPs are marked with red. So generally, you can see that they form sort of distinctive groups. Then a few words about distances. So generally, BLAPs are distant objects. All of the parallaxes are below 1 milli arc second, and these are objects from the work that from the inner bulge, and you can see that most of the objects are actually belong to the bulge population, and this is the OGLE BLAP 001, which is actually in the disk. So then a few words about the current research. So generally, the whole inner bulge was checked for periodicity in two ways. So over the whole light curves and season by season to check whether there are any objects with significant period changes. And as the result, there were 90 BLAPs were found. And also, maybe I didn't mention this previously, but during the researches in the outer bulge and disk, there were some hundreds of additional variables with like low amplitude and sinusoidal light curves. And actually, we didn't classify them because it would be challenging using only photometry. Probably most of these objects are Delta Scuti stars, but there may be some interesting objects around them, and but for now we didn't do anything with them. And here you can see that generally the inner bulge research is more complete because we generally have more measurements, but also BLAPs tend to cluster in the inner bulge. So you can see that our research is complete to more or less 18.5 magnitude in the I band. And generally, Yeah, maybe because it's, as you can see from the period amplitude diagram for all of the BLAPs, this is quite important. Like this, from this diagram, you can see how we would classify those objects. So we have like three types of light, the classical ones. So this is, for example, like BLAP 95, 96, 97, generally this type of light have a sharp maximum. Also similar to original 14 objects. Then there is the bump one. So this actually is quite an unusual effect, which you can see, for example, in object like BLAP 100, BLAP 98, BLAP 107. So this actually, this feature is not observed in the delta Scuti stars. So these objects we have, for example, previously, as I was showing, this, for example, you have spectrum for this object, which also has this bump, and this we also have a spectrum for example, for this object. So generally, which also shows this kind of bump, and for this object, if I'm correct. So generally, the spectra of these objects confirmed that they are BLAPs, and on this plot here with the empty marks, you can see which objects have are spectroscopically confirmed. So generally, you can see that for the longer period objects, we only classified the objects with some feature in their light curve, because it is at these periods and these amplitudes we have a lot of delta Scuti stars, so it would be difficult to distinguish between them if they didn't have like a typical light curve. Then there is also the deep light curves. So there, generally some of the BLAPs, for example, BLAP 009 is the best example. You can see this. There is a small dip around the maximum in the light curve. So this is also another type of light curve that could be separated, and these objects generally tend to cluster in here. And you can see from this plot that it could be deduced that the BLAP amplitude increases as the pulsation period is decreasing, but as I was saying, we actually have a lot of variables from this area, but it's difficult to classify them. And also a few words about the lower amplitude regime. So we have some objects with lower amplitudes. We actually have a lot of, for example, objects with like amplitudes, as I was saying, have like few thousands probably of such objects, but we don't know if we could classify them as BLAPs, because generally, for example, this object, we have spectrum because this is this one. So it was, as you can see, the light curve is has this bump. So that's why this object was taken for spectra. But actually, there are some plans to get spectra for some of the other objects from like this area. Yeah, so here, for example, you have some objects that are actually turned out to not be BLAPs. So these are the ZGP candidates from the 2022 work. And actually, this stars turned out to be a delta Scuti or S6 Finis stars, because they have like temperatures around 10,000 K. So they are actually not BLAPs. And for these objects, maybe this is they have like they are typical light curve for a delta Scuti star. This object is interesting, but actually it turned out that this is not BLAP. So and yeah, and all of these objects are blue. So this probably indicates that they are actually closer than because they are not reddened. So now a few words about estimating the completeness of our research. So beside the idea of classification bias, there is also I try to estimate how complete are these searches in different areas. So actually to check whether we found even like the objects, whether. So here you have an example of a real and simulated light curve and a frequency spectrum. So you can see we could somehow recreate the aliases, and that would like lead us to proper estimation of the signal to noise ratio. And then you have some obvious effects. So as you can see, as the light curve gets less bright, you have more scattering. So it is difficult to classify because the noise is getting too high. And then you have also other effects. So the OGLE deep survey has a observation time of 100 seconds in the I-band. So you can see that if the period is getting shorter and is approaching this 100 seconds, you can see that the amplitude decreases, the observed amplitude, obviously. So then here are the results of those simulations. So these are done for typical light curve of OGLE BLAP 014 with like 0.3 magnitude amplitude. So generally, you can see that we are at around 100 points. We are complete to some 90.5 or 90 magnitude. And actually, the OGLE for fields that had less than 50 points, because there were some were not even checked, because it would be completely random to say whether the star was variable or just that it would be a scatter of some random points. So a few words about some other interesting objects. Here you have example of two extreme helium stars, pulsating extreme helium stars. These are the only two known. So these were actually found by spectroscopy, and they have very low hydrogen content with like 1% or something like that. And we have some objects that could be similar, or maybe like have at least sort of similar light curves. And this objects pulsate with around 2-hour periods, and these objects actually the bump in the light curve is attributed to supersonic shocks, and maybe these objects are somehow connected to the extreme helium stars. And then there are the objects that I was talking about that we are not sure whether to classify them as BLAPs or delta Scuti. So you can see that we have a lot of, this is just example, but we have like hundreds of light curves that look like this and have just too long of a period to be attributed, to be like classified as BLAPs with high certainty. And then there is example of one object that has actually light curve with a bump, but and has a longer period than most of the BLAPs, but generally this object has a large rate of period change, and also this object has a very high amplitude for this long of a period. So generally it is scheduled for spectroscopy, but for now we couldn't classify it. Then there is the shortest period variable detected in the OGLE data. So this object was detected in the inner bulge with period slightly more than 4 minutes. So this is for now the shortest period variable from OGLE. And we also don't know, we didn't classify it. So generally we also have it scheduled for spectra. Then there are some other interesting objects that were found. So here are examples of some short period eclipsing binaries. So you have like two typical HW Virginis light curves with a strong reflection effect. And also this is very interesting object because the light curve resembles contact binary, but this is way too short of a period for a contact binary, or at least for the known contact binaries. So this object is also interesting. Also, it appears to be red, but this is not certain because it has there is a other star nearby, so the color is not this is not obvious whether this is really a red star. And also there are some variables that have X-ray counterparts. So this object was actually known previously. This is supposed to be a rotation period of a white dwarf in an intermediate polar, and but actually this is only light curve from one season, and we have, because this is one of the fields with the highest cadence. So we have a much more detailed light curve, and also there are new objects that were not classified as an X-ray counterpart. So they show some kind of periodicity, but it is difficult to say. But they are like probable X-ray counterparts in the bulge. A few words to summarize. So OGLE discovered 184 BLAPs in total by checking all of the data set of 2 billion stars. And the periods are from like 3 to 70 plus minus, and the amplitudes are up to 0.45 magnitude. BLAPs represent diverse light curve shapes, as I was showing. The BLAPs are hot counterparts of classical pulsators. This means that they have giant-like structures, so most of the mass is concentrated in the core, and the envelope is quite thin. And it is expected that they follow period luminosity relation. As we saw from the map, BLAPs concentrate around the galactic plane. We didn't find any objects in the Magellanic Clouds, and also during the years, no BLAPs were found in the globular clusters, and these were surveyed quite a lot. And we also found, as I was saying, additional objects that for now are unclassified, but maybe we will do something with them in the future. Okay, so that is it.
Thank you very much. Thank you, Joachim. Super. And do we have any questions or comments? So I have a question because as there is no BLAPs in Magellanic Clouds, do you think it's rather a bias, like kind of observational bias, or may it depend on, I don't know, metallicity or anything like structure?
Well, it could be observational bias because, of course, the Magellanic Clouds are farther than the typical BLAPs, but if the BLAPs have like around 200 solar luminosity, I think that we would see them. Okay. So I generally think that this is not an observational bias, at least if they display the typical luminosity.
And any comment on the metallicity? How much could, I don't know, the evolution depend on metallicity?
Well, this depends on the model. Okay. I mean, the models, all of the models, actually, they take this into account, but as you could see, there were like few formation scenarios, so it depends which scenario we think is the correct one.
But as I understand, the third scenario, so double white dwarf is thrown away right now because of the number, right? Because you said it was...
Yes, maybe it's not thrown away, but it couldn't explain the whole sample. Because they said that this, like, their simulations are correct, and this is like sure that BLAPs could emerge from this scenario, but maybe this is the fraction. We still don't know if the BLAPs are like have all of the BLAPs have the same origin. We don't know this. So
thank you very much. Any? Martin?
So to this time there are no measurements of mass.
No direct, yes, because Well, we have only one object in like close binary, and I'm not sure if somebody attempted the mass measurement, so we don't have any direct measurements of mass. And generally, for example, the OGLE BLAP 009, there was this idea that they checked this object very thoroughly, but they estimated the mass from some like spectral energy distribution. So this is not a direct measurement or anything. And also they overlapped this with some models. So this was like the value that they got, but this heavily depends on the models. So.
Okay, I don't see anything on Zoom. So if there is no more questions, let's thank Joachim again. Thank you. And next week, we have a guest from Germany, Marlene Latour, that's going to tell us about the global clusters. And also don't forget to put your name in the notebook. Thank you very much. Dziękuję. Bardzo ciekawe.